Space has an edge. That is what they told you. A boundary where everything stops. A cosmic wall where existence ends. For centuries, we imagined the universe as a finite stage with curtains drawn at the limits of reality. But physicists discovered something that shattered this comfortable illusion. There is no edge, no wall, no boundary where the cosmos simply stops. The answer to what lies beyond space is so profound, so paradigm-shattering, that it forces us to rewrite every assumption about existence itself. This revelation changes everything, from the fate of galaxies to the meaning of your place in the cosmos, from the nature of time to whether we are truly alone. If you are ready to discover what truly lies at the limits of reality, hit that like button and subscribe. The question itself is flawed. What lies beyond the edge of space? The question assumes space has an edge. It does not. The universe does not have a physical boundary, no fence marking the end of existence, no cosmic stop sign declaring you cannot pass. This is not philosophy. This is physics screaming at us from the data. For 13.8 billion years, space has been expanding, stretching, inflating like a balloon that never stops growing. But here is where your intuition breaks down. When a balloon expands, it expands into something, into a room, into air, into space. The universe? It expands into nothing. It creates space as it goes. Imagine standing on the surface of Earth. You walk in a straight line, north, south, east, west. It does not matter. You never reach an edge. You never fall off. You circle back. The surface is finite, but has no boundary. The universe could work the same way, but in 3 dimensions, or 4, or more. You could travel in a straight line forever and never hit a wall because there is no wall to hit. Cosmologists call this the possibility of a closed universe, a cosmos that curves back on itself like the surface of a sphere. The alternative? An infinite universe. No edge because there is no end. Space extending forever in all directions, galaxies beyond galaxies, stars beyond stars, stretching into eternity. But wait, you have seen images, diagrams, illustrations showing the observable universe as a sphere, a bubble, a limited region. What is that if not an edge? This is where the revelation gets brutal. That boundary is not the edge of space. It is the edge of what we can see. It is the edge of information, not existence. Light travels at a finite speed, 186,000 miles per second. Fast, but not infinite. The universe is 13.8 billion years old. That means light from the earliest moments of the cosmos has only had 13.8 billion years to reach us. Anything farther, we cannot see it. Not because it is not there, because the light has not arrived yet. Here is the twist. Because space itself is expanding, that distant light has been traveling through expanding space. The result? The edge of the observable universe is not 13.8 billion light-years away. It is 46.5 billion light-years away. The observable universe is a sphere 93 billion light-years across, centered on Earth. But Earth is not special. Every point in the universe has its own observable sphere. An alien standing on a planet 50 billion light-years away has their own 93 billion light-year bubble. Their observable universe overlaps with ours, but also extends into regions we will never see. Their edge is not our edge. There is no universal edge. The math is relentless. According to calculations, the current co-moving distance to particles from which the cosmic microwave background radiation was emitted is about 45.7 billion light-years. The cosmic microwave background, the faint afterglow of the Big Bang, represents the farthest back in time we can observe. It is the baby picture of the universe, taken when the cosmos was only 400,000 years old. Beyond that, a wall of light. Not because space ends, because before that moment, the universe was so hot and dense that light could not travel freely. It was trapped. We are looking at a horizon, not an edge, like standing on a ship in the ocean. You see water meeting sky. You call it the horizon. But you absolutely know, there is more ocean beyond it. Scientists confirm this with the cosmological principle. The principle states that the universe looks roughly the same in all directions. We see the cosmic microwave background in every direction, galaxies in every direction, large-scale structure in every direction. We are not in a special location. We are not at the center. If the universe truly ended at the edge of what we observe, we would be sitting exactly in the middle of everything. What are the odds? Astronomically, impossibly small. The evidence points to one conclusion. There is more universe beyond our horizon. Much more. Possibly infinitely more. This is not speculation. This is the only explanation consistent with observation. Unless you believe that Earth, our solar system, our galaxy, just happens to occupy the exact center of a finite universe that ends precisely where our telescopes stop seeing. That would require a level of cosmic coincidence that violates every principle of modern science. The universe does not care about us. It does not arrange itself around our vantage point. What we see is a tiny local sample of something vastly, incomprehensibly larger. Now the question shifts. If the observable universe is just a bubble, a limited view, a horizon we cannot cross, what lies beyond it? More space? Different space? Other universes? The answer depends on the shape, the topology, the ultimate structure of reality itself. And that is where the science gets wild. Because the implications are staggering. If space is infinite, then every possible configuration of matter must repeat. Somewhere out there, far beyond the observable horizon, there is another Earth, another you. Reading these exact words, if space is finite but boundless, curved back on itself, then traveling far enough in one direction brings you back to where you started. The universe as a cosmic loop. But there is more, much more, because the edge of what we can see is not fixed. It is moving, changing, evolving with time. As the universe ages, more light reaches us. In principle, we should see more galaxies, more stars, more cosmic structure as time goes on. But here is the nightmare. The universe is not just expanding, it is accelerating. Dark energy, a mysterious force that makes up 70% of the universe, is pushing space apart faster and faster. Galaxies beyond a certain distance are receding from us faster than light can travel through the expanding space between us. We will never see them, ever. They are crossing a different kind of horizon. The cosmic event horizon. The cosmic event horizon is the boundary beyond which any signal sent now will never reach us. It is approximately 16 billion light years away. Galaxies beyond that distance, lost forever. Their light will never reach Earth. They are not leaving the universe. They are leaving our universe, our observable bubble, our patch of reality. Every second, more galaxies slip beyond this horizon. Every second, the observable universe is losing matter. Not because the universe is shrinking, because it is expanding so fast that distant regions are being severed from us, cut off, isolated by the stretching fabric of space itself. This is not science fiction. This is happening right now. galaxies are vanishing from view. The universe is becoming lonelier, and we are powerless to stop it. But what they discovered next was even stranger, because the edge of space, the limits of observation, the horizons that define what we can and cannot see, are not just features of cosmology. They are features of reality itself. And understanding them requires confronting the most disturbing possibility of all, that beyond our observable universe lies something we never expected, something that challenges the very concept of beyond. The question is no longer, what lies beyond the edge of space? The question is, does beyond even mean what we think it means? And that question leads us directly to the ancient myths, the early maps, the historical obsession with cosmic boundaries that haunted humanity for millennia. For thousands of years, humanity lived with a comforting lie. The universe had walls, boundaries, an edge you could reach if you traveled far enough. Ancient civilizations stared at the night sky and saw a dome, a ceiling, a cosmic shell enclosing reality. The stars were not distant suns scattered through infinite space. They were lights embedded in a crystalline sphere rotating above the Earth. This was the celestial sphere, the sphere of fixed stars, the firmament. It was the supposed limit of the entire universe. Beyond it, nothing. Void. The end of existence itself. The ancient Greeks formalized this vision into philosophy and science. Pythagoras and his followers constructed cosmologies where the stars occupied the outermost boundary of reality. Philolaus, a Pythagorean philosopher in the 5th century BC, imagined a universe with a central fire at its core, invisible to humans. The Earth, Moon, Sun, and planets orbited this fire, and beyond them all was the sphere of fixed stars, the final boundary. It rotated, but so slowly that motion was imperceptible. The stars were frozen in place, eternal, unchanging, locked in their positions on the cosmic shell. Plato took this further. His universe was a series of concentric spheres nested inside one another like Russian dolls. At the center sat the Earth, completely stationary. Around it, spheres of fire carried the moon, sun, and planets. The outermost sphere, the largest and most distant, was the sphere of fire that held the stars. This sphere rotated around the Earth, dragging the stars with it. The stars were fixed. Their positions relative to one another never changed. This fixedness was essential to Plato's entire system. The stars served as a reference frame, a cosmic map, a stable backdrop against which all other celestial motions could be measured. This was not mythology. This was science. The best minds of the ancient world believed it. For centuries, it defined human understanding of the cosmos. Aristotle built on Plato's work and crystallized the geocentric model into a comprehensive physics that dominated intellectual thought for over 1,000 years. The universe was finite, bounded, enclosed. Space ended at the sphere of the fixed stars. Beyond, the concept had no meaning. There was no beyond. The sphere was the edge, the wall, the final barrier. The universe stopped there. But cracks appeared, slowly, subtly. New stars blazed into existence. Novas. Ancient Chinese astronomers documented them. Greek observers noted them. The stars were supposed to be fixed, eternal, unchanging. New stars suggested otherwise. But novas faded after weeks or months, disappearing back into darkness. The phenomenon was unexplained, mysterious, unsettling. It hinted that the heavens were not as unchanging as the models claimed. Yet the celestial sphere model survived. It was too elegant, too useful. too deeply embedded in the cultural and intellectual framework to abandon over a few anomalies. Then came the Copernican revolution. In the 1540s, Nicolaus Copernicus proposed a radical idea. The Earth was not the center of the universe. The Sun was. The Earth moved. The planets orbited the Sun. This shift was seismic. It shattered the nested spheres, the stationary Earth, the cosmic hierarchy that placed humanity at the center of creation. But Copernicus still retained the sphere of fixed stars. The stars remained fixed, distant, on an outer boundary. The universe still had an edge. The death blow came from proper motion. In 1718, Edmund Halley announced a discovery that destroyed the concept of fixed stars forever. He compared observations of stars made by ancient astronomers like Hipparchus and Ptolemy with more recent data from Tycho Brahe and others. 4 stars had moved, not because the Earth moved, not because of observational error. The stars themselves had changed position relative to one another. The stars were not fixed. They were in motion, drifting through space. The celestial sphere did not exist. Jacques Cassini confirmed it. He corrected Brahe's observations, compared them with his own measurements, and provided the first definitive evidence of stellar proper motion, specifically for the star Arcturus. The stars were not embedded in a rotating shell. They were scattered through 3-dimensional space at vastly different distances. The fixed stars were not fixed. The sphere was an illusion created by the limits of human vision, the inability to perceive depth across astronomical distances. Parallax measurements in the 1830s confirmed what proper motion had suggested. Stars were not equidistant. They were near and far, close and remote, distributed through a volume of space so vast it defied comprehension. The universe did not have a shell. It did not have walls. The edge humanity had believed in for millennia vanished. Reality opened up. The cosmos was not a cozy, enclosed room with a ceiling. It was an abyss, infinite, unbounded, terrifying. The psychological impact was profound. For thousands of years, humans lived inside a universe with edges, with limits, with structure. The celestial sphere gave meaning to the cosmos. It defined up and down, inside and outside, here and there. Removing the sphere removed the boundaries. The universe became an infinite void, and humanity was not at the center. We were floating in a meaningless expanse with no walls, no reference, no cosmic architecture to orient ourselves. But the question did not disappear. It transformed. If the stars were not on a sphere, where did space end? Did it end? Early modern astronomers had no answer. The universe expanded conceptually from a finite sphere to an infinite expanse, but the question of boundaries lingered. What replaced the celestial sphere? What defined the edge of reality? The 20th century delivered an answer, but it was not the answer anyone expected. Einstein's theory of general relativity revealed that space itself could be curved, warped by mass and energy. The universe could be finite yet unbounded, like the surface of a sphere. No edge, but also not infinite. Or it could be infinite, stretching forever in all directions. The universe could have different shapes, different topologies, different geometries. The flat, Euclidean space of everyday experience might not apply to the cosmos as a whole. Then came Hubble. In the 1920s, Edwin Hubble discovered that the universe was expanding. Galaxies were moving away from each other. Space itself was stretching. The cosmos was not static, not fixed, not eternal. It had a beginning, the Big Bang, and it had a history. This discovery introduced a new kind of edge. not a spatial boundary, but a temporal one. A horizon defined by the finite age of the universe and the finite speed of light. The ancient dream of a universe with walls was dead, but it left a legacy. The human mind craves boundaries. We need edges to make sense of space. Without them, the universe feels incomprehensible, overwhelming, existentially threatening. The celestial sphere was wrong, but it was psychologically necessary. It gave structure to the cosmos. Its removal forced humanity to confront a reality far stranger, far larger, far more alien than anything imagined by the ancients. And now the question returns, not as ancient cosmology, as cutting-edge physics. What defines the boundary of the universe? What replaces the sphere of fixed stars? The answer lies in the concept of horizons, multiple kinds of horizons, each marking a different kind of edge. And understanding them requires diving into the mathematics of expanding space, the geometry of space-time, and the brutal reality of cosmic acceleration. Because the universe does not have one edge, it has many, and they are all moving. The universe you see is not the universe that exists. What you observe is a bubble, a sphere, a limited local sample of reality centered exactly on you. This is the observable universe, and it has a radius of 46.5 billion light-years. That number is critical. That number defines everything you can ever hope to see, detect, or measure. Beyond that distance, darkness, not because space ends, because information ends. Here is the paradox that breaks most people's brains. The universe is 13.8 billion years old. Light has been traveling toward Earth for 13.8 billion years. So the edge of the observable universe should be 13.8 billion light-years away, right? Wrong. It is 46.5 billion light-years away. How? The math seems impossible. Light traveling for 13.8 billion years should only cover 13.8 billion light-years. That is what a light-year means. The distance light travels in 1 year. But the universe does not play by static rules. Space itself expands. Imagine a photon leaving a distant galaxy 13 billion years ago. It travels toward Earth at the speed of light, 300,000 kilometers per second. Nothing in the universe moves faster. But while that photon races through space, space itself stretches. The galaxy that emitted the photon moves farther away, not because it is traveling through space, but because space between the galaxy and Earth is expanding. The photon is like a runner on a treadmill that keeps getting longer. The runner moves forward, but the finish line keeps receding. This is not science fiction. This is general relativity. Space is not a fixed stage. It is a dynamic fabric that stretches, warps, and curves. Objects are not racing through space. Space is pulling them apart. Think of a balloon with dots drawn on its surface. As you inflate the balloon, the dots move apart, not because they are sliding across the rubber, because the rubber itself is expanding. The dots are galaxies. The rubber is space. The expansion rate is not constant. It changes over time. Early in the universe's history, space expanded slowly, then faster, then even faster. The current expansion rate is approximately 0.007% per million years for any given distance. That sounds tiny. It is not. For galaxies separated by 20 billion light-years, that 0.007% translates to 1.4 million light-years of new space created in just 1 million years. That is faster than light, much faster. But it does not violate relativity because the galaxies are not moving through space. Space itself is growing. Now back to the photon. It leaves a galaxy 13 billion years ago and travels toward Earth. During those 13 billion years, the galaxy continues moving away as space expands. By the time the photon reaches Earth, the galaxy is no longer where it was when the photon left. Calculations show that the galaxy is now 46 billion light-years away. The photon traveled through expanding space, and the expansion stretched the distance behind it. The light took 13.8 billion years to arrive, but the source is now 46.5 billion light-years away. This is the observable universe, a sphere 93 billion light-years across. It represents the maximum distance from which light has had time to reach Earth since the Big Bang. But it is not an edge, it is a horizon, like standing on a ship in the middle of the ocean. You see water meeting sky. You call it the horizon, but you know there is more ocean beyond it. You just cannot see it yet. The observable universe works the same way. There is more universe beyond the horizon. You just cannot observe it. The light has not arrived yet. Here is where it gets brutal. The horizon is not the same for everyone. Every observer has their own observable universe. An alien on a planet 50 billion light-years from Earth has a completely different horizon. Their observable universe is a sphere 93 billion light-years across, centered on them. Parts of their observable universe overlap with ours. Other parts do not. They can see galaxies we will never see. We can see galaxies they will never see. There is no universal edge. There is no absolute boundary. Every point in space is the center of its own observable sphere. The most distant objects we observe are not galaxies. They are photons. Ancient photons from the cosmic microwave background, the CMB. The CMB is the afterglow of the Big Bang. Radiation emitted when the universe was only 383,000 years old. Before that moment, the universe was too hot, too dense. Electrons and protons floated freely in a plasma so thick that light could not travel. Photons scattered constantly, trapped in an opaque fog. Then the universe cooled. Electrons and protons combined to form hydrogen atoms. The fog cleared. Light traveled freely for the first time. That light has been traveling ever since. When we detect the CMB, we are looking back in time 13.8 billion years, seeing the universe as it was 380,000 years after the Big Bang. But the conmoving distance to the source of that radiation is not 13.8 billion light-years. It is 46 billion light-years. The region of space that emitted the CMB has been moving away from us for 13.8 billion years due to cosmic expansion. It is now on the far edge of the observable universe. This is the particle horizon, the boundary beyond which no particles or light signals have had time to reach us. The particle horizon is not a wall. It is a limit of information. Beyond it lies space we cannot observe because the light has not arrived yet. But the space exists. The galaxies exist. The stars exist. We just cannot see them. The observable universe is like looking at a photograph of a crowd. You see the people near the camera. The people at the edge of the frame are blurry or cut off, but you know more people exist beyond the edges of the photograph. The photo is limited by the camera's field of view. The observable universe is limited by the speed of light and the age of the cosmos. This creates a deeply unsettling reality. Most of the universe is invisible, forever. The vast majority of space lies beyond our horizon, and always will. As the universe ages, we should see more galaxies, more stars, more structure. The horizon should expand as light from farther regions reaches us. But it does not work that way, because the universe is not just expanding, it is accelerating. Dark energy, the mysterious force driving cosmic acceleration, changes everything. Galaxies beyond a certain distance are receding faster than light can travel through the expanding space between them and Earth. Light from these galaxies will never reach us, ever. They are crossing a different horizon, the cosmic event horizon. This horizon is approximately 16 billion light-years away. Galaxies beyond this distance are lost, not because they disappeared, because they are moving away so fast that no signal they send now or in the future will ever reach Earth. This is the terrifying truth. The observable universe is not growing, it is shrinking. Every second, galaxies slip beyond the event horizon. Every second, more of the cosmos becomes unreachable. Dark energy is isolating us, severing our connection to distant regions of space. In trillions of years, every galaxy outside our local group will vanish beyond the horizon. Future civilizations will look at the sky and see nothing but a handful of nearby stars. They will conclude the universe is small, empty, static. They will be wrong, but they will have no way to know. The observable universe is not a boundary of space. It is a boundary of knowledge, a horizon defined by light, time, and the relentless expansion of the cosmos. What you see is not what exists. What exists is incomprehensibly larger, and most of it will remain forever hidden, forever unreachable, forever beyond the limits of observation. But here is the question that keeps physicists awake at night. If the observable universe is just a tiny bubble in a vastly larger cosmos, what determines the size of that larger cosmos? Is the universe beyond our horizon infinite, finite, curved, flat? Does it loop back on itself? And how do we possibly answer these questions when we cannot see beyond the edge of observation? That is where the geometry of space-time, the mathematics of cosmic expansion, and the concept of multiple horizons become absolutely critical. Because the universe does not have one edge, it has many, and they are all moving. Space does not sit still. It never has. Since the moment the universe began, space has been expanding, stretching, inflating outward in all directions. This is not objects moving through space. This is space itself growing, creating new distance between galaxies, stars, and every point in the cosmos. The fabric of reality is elastic. It stretches, it warps, it expands. Imagine a balloon. Draw dots on its surface with a marker. Now inflate the balloon. The dots move apart, not because they are sliding across the rubber, because the rubber itself is expanding. The dots represent galaxies. The rubber represents space. As the balloon inflates, every dot moves away from every other dot. There is no center. Every dot sees all the other dots receding. The universe works the same way. This is the revelation that destroyed static cosmology. In 1929, Edwin Hubble measured the light from distant galaxies and discovered something impossible. The farther a galaxy was from Earth, the faster it was moving away. Not because galaxies were racing through space, because space between galaxies was expanding. Hubble's law emerged from the data. Velocity equals distance multiplied by the Hubble constant. The implication was brutal. The universe had a history. It was smaller in the past, much smaller. And if you ran the clock backward far enough, everything collapsed to a single point, the Big Bang. But expansion is not constant. It changes over time. Early in cosmic history, space expanded slowly, then faster, then even faster. The current rate is approximately 70 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space expands by 70 kilometers every second. It sounds small. It is not. For galaxies separated by billions of light-years, the expansion rate exceeds the speed of light. Wait, nothing can move faster than light. That is the law. Einstein proved it. Correct. Nothing can move through space faster than light. But space itself has no speed limit. Space can expand as fast as it wants. Relativity does not care. The speed of light limit applies to objects moving through space, not to space itself. This is the loophole. This is how galaxies billions of light-years away are receding from Earth, faster than 300,000 kilometers per second. The expansion is not smooth. It is not uniform across all scales. Gravity fights back. On small scales, gravity wins. The atoms in your body are not expanding. The Earth is not expanding. The solar system is not expanding. The Milky Way is not expanding. Gravity holds these structures together. The electromagnetic force holds atoms together. Expansion only dominates on the larger scales, where gravity is too weak to resist. Galaxy clusters are expanding. Superclusters are expanding. The cosmic web, the large-scale structure of the universe, is being stretched apart. The driving force behind this expansion? Unknown. Physicists call it dark energy, a placeholder name for something we do not understand. Dark energy makes up 70% of the universe. It is everywhere. It fills space. It does not clump, does not interact, does not decay. It just pushes. It accelerates the expansion. The more space expands, the more dark energy appears. More dark energy means faster expansion. Faster expansion means more space. More space means more dark energy. It is a runaway process. The universe is accelerating into oblivion. This acceleration was discovered in 1998 by two teams studying distant supernovae. The supernovae were dimmer than expected, meaning they were farther away than predicted. The universe was not just expanding, it was speeding up. The discovery won the Nobel Prize. It also destroyed the old models. Physicists expected expansion to slow down over time due to gravity. Instead, it was accelerating. Dark energy rewrote cosmology. It changed the fate of the universe. It made the cosmos finite in observability, even if infinite in extent. Here is the nightmare. Acceleration means galaxies beyond a certain distance are receding faster than light can bridge the gap. Light from these galaxies will never reach Earth. They are beyond the cosmic event horizon. This horizon is approximately 16 billion light-years away. Every second, more galaxies cross this boundary. Every second, the observable universe loses matter. In the far future, every galaxy outside the local group will disappear beyond the horizon. The universe will appear empty, dark, static. Future astronomers will have no evidence of the Big Bang, no evidence of expansion, no evidence of the vast cosmos we observe today. The expansion of space is not a theory. It is an observed fact. It is measured. It is quantified. It defines the structure and fate of reality. And it creates a boundary not of space, but of information. The cosmic event horizon is the ultimate edge, the final limit of what can ever be observed, no matter how long we wait. But expansion raises deeper questions. If space is expanding, what is it expanding into? Does that question even make sense? And if the observable universe is just a bubble in a vastly larger cosmos, what lies beyond? More space, different physics, other universes? The answer depends on the shape of space-time itself, the topology of the cosmos, and the existence of multiple kinds of horizons. And that is where the science becomes truly strange. The universe has edges, multiple edges, not walls, not boundaries where space stops, horizons, lines in space-time that separate what we can observe from what we cannot. Each horizon marks a different limit, a different kind of boundary, a different reason why information fails to reach us. Understanding these horizons is understanding the true structure of the cosmos. The particle horizon is the first edge. It defines the maximum distance from which light has had time to reach us since the Big Bang. This horizon is approximately 46.5 billion light-years away. Everything within this sphere has had enough time to send a signal to Earth. Everything beyond it has not. The particle horizon grows as the universe ages. Every second, light from slightly farther regions reaches us. The observable universe expands. But there is a catch. The expansion of space works against this growth. The cosmic event horizon is the second edge. It marks the boundary beyond which any signal sent now will never reach us. This horizon exists because space is expanding faster than light can travel through it at larger distances. The event horizon is approximately 16 billion light-years away. Galaxies beyond this distance are lost forever, not because they disappeared, because the space between them and Earth is growing too fast for light to bridge the gap. Every second, galaxies cross this horizon. Every second, the universe becomes more isolated. The Hubble sphere is the third edge. It defines the distance at which the recession velocity of space equals the speed of light. At this boundary, galaxies are moving away from us at exactly 300,000 kilometers per second due to cosmic expansion. The Hubble sphere is not the same as the event horizon. Light from beyond the Hubble sphere can still reach us if it was emitted in the past, when the universe was expanding more slowly. But galaxies currently beyond the Hubble sphere are receding faster than light, and any signal they send now will struggle to reach Earth. These horizons are not physical objects. They are mathematical boundaries defined by the geometry of space-time, the age of the universe, and the rate of cosmic expansion. They move, they change, they evolve as the cosmos ages. In the early universe, the particle horizon was small. Only nearby regions could communicate. As time passed, the horizon grew. More of the cosmos became observable. But dark energy changed everything. Dark energy drives accelerated expansion. It pushes galaxies apart faster and faster. As acceleration continues, the event horizon shrinks. More galaxies slip beyond the boundary of observability. In trillions of years, every galaxy outside the local group will vanish beyond the horizon. The observable universe will collapse to a handful of nearby stars. Future civilizations will see an empty cosmos and conclude the universe is small, static, eternal. They will be wrong, but they will have no evidence to prove otherwise. The surface of last scattering is another critical boundary. It marks the moment when the universe became transparent to light, 380,000 years after the Big Bang. Before this moment, the cosmos was an opaque plasma. Photons scattered constantly, trapped in a dense fog of particles. After this moment, electrons and protons combined to form neutral hydrogen. The fog cleared, light traveled freely. The cosmic microwave background, the CMB, is the light from this surface. It is the oldest light in the universe. We see it in every direction. A faint glow at a temperature of 2.7 Kelvin. The CMB is a horizon. We cannot see beyond it, not because space ends there, because the universe was opaque before that moment. These horizons define the limits of observation, but they do not define the limits of existence. The universe beyond the particle horizon is just as real as the universe within it. We just cannot see it. The evidence points to this conclusion. The cosmic microwave background is uniform in all directions. The large-scale structure of the universe is homogeneous. We are not in a special location. If the universe truly ended at the edge of the observable sphere, Earth would be at the exact center. The odds are astronomically small. So what lies beyond the horizons? More space, more galaxies, more stars, possibly infinitely more. If the universe is infinite, then every possible configuration of matter must repeat somewhere beyond our horizon. Another Earth, another you. Reading these exact words, if the universe is finite but unbounded, then it curves back on itself like the surface of a sphere. Traveling far enough in one direction brings you back to where you started. The shape of the universe determines what lies beyond. Flat space extends forever. Closed space loops back. Open space curves outward infinitely. Current measurements suggest the universe is flat, or very close to flat. Flat means infinite. Infinite means no edge, no boundary, no end. But there is more, much more. Because the concept of beyond itself might be flawed. What if the universe is not embedded in a larger space? What if there is no outside to the cosmos? That question leads directly to the deepest mystery. What does it mean for something to exist beyond space? And how do we even begin to answer that question when the very concept of beyond assumes a framework that might not apply to reality? The universe beyond the horizon is not what you think. It is not just more galaxies, more stars, more of the same cosmic structures we observe nearby. The physics could be different. The laws could change. The fundamental constants that govern reality, the strength of gravity, the charge of the electron, the speed of light, could have completely different values. This is not speculation. This is what the mathematics of modern cosmology predicts. Eternal inflation theory suggests the Big Bang was not a singular event. It was one bubble in a vast inflating multiverse. Space inflates at an exponential rate, doubling in size every fraction of a second. In most regions, inflation never stops. It continues forever, creating infinite volumes of space. But in some regions, inflation slows down, stops, and a universe like ours forms. A bubble, a pocket, a localized region where the laws of physics stabilize and galaxies can form. Our observable universe is one such bubble. Beyond our horizon, inflation may still be raging, creating new bubbles, new universes, new domains of reality. Each bubble has its own physics, its own constants, its own laws. In some bubbles, gravity is too strong. Matter collapses instantly. No stars, no galaxies, no life. In other bubbles, gravity is too weak. Matter never clumps. No structure forms, just a cold, diffuse gas expanding forever. Our bubble has the right constants, the right balance, the right conditions for complexity. This is the multiverse. Not science fiction, not philosophy. A direct consequence of inflation theory, one of the most successful frameworks in modern cosmology. Inflation explains why the universe is flat, why the cosmic microwave background is so uniform, why large-scale structure looks the way it does. But inflation also predicts eternal inflation, and eternal inflation predicts a multiverse. If inflation happened once, it happened everywhere. And if it happened everywhere, it created infinite bubbles, infinite universes, infinite variations of physical law. The terrifying part: we can never observe these other bubbles. They are beyond our horizon, beyond our event horizon, beyond any possible measurement. The speed of light and the expansion of space ensure we remain isolated inside our bubble, forever separated from the rest of the multiverse. We see only our local patch of reality. We measure only our local physics. The vast structure beyond, hidden, inaccessible, unknowable. But there is indirect evidence. The cosmic microwave background contains anomalies, cold spots, unexpected patterns that could be scars from collisions with other bubble universes in the early moments of our cosmic history. Some physicists argue these anomalies are statistical flukes. Others claim they are smoking gun evidence of a multiverse. The debate rages. The data is ambiguous. The implications are staggering. String theory adds another layer. In string theory, the fundamental building blocks of reality are not particles. They are tiny vibrating strings of energy. The way a string vibrates determines what particle it becomes. An electron, a quark, a photon. But string theory requires extra dimensions. Not the 3 dimensions of space and 1 of time we experience. 10 dimensions, 11 dimensions, maybe more. The extra dimensions are curled up, compactified, too small to detect. But the way they curl determines the physics of the universe. There are trillions of ways to curl extra dimensions. Each configuration produces a different universe with different laws. This is the string theory landscape, a vast space of possible universes, each real, each existing, each isolated from the others. Our universe is one point in this landscape. Beyond our horizon, other points exist, other configurations, other realities. Quantum mechanics offers yet another possibility. The many worlds interpretation suggests every quantum event splits the universe into multiple branches. Every time a particle decays, every time a photon is emitted, every time a measurement is made, the universe splits. One branch where the particle decayed, another where it did not. Both branches are real. Both exist. Both continue evolving. The number of branches is infinite. The multiverse is not separate bubbles in space. It is separate branches in quantum possibility space. The math works, the predictions hold, but the philosophical implications are brutal. If the multiverse exists, then everything that can happen does happen. Somewhere. There are universes where you made different choices. Universes where history unfolded differently. Universes where the laws of physics are alien, incomprehensible, hostile to life. And we are trapped in one branch, one bubble, one configuration. Forever isolated. Forever limited to our local patch of reality. Critics argue the multiverse is not science. It is not testable. It makes no falsifiable predictions. If we can never observe other universes, how can we claim they exist? But defenders counter that the multiverse is a prediction of successful theories like inflation and string theory. We do not test the multiverse directly. We test the theories that predict it. And those theories work. The question is no longer, what lies beyond the edge of space? The question is there even an edge to lie beyond? Because if the multiverse is real, then our universe is just one bubble in an infinite foam of realities. The edge of our observable universe is not the edge of existence. It is just the edge of what we can see. Beyond lies something far stranger, not empty space, not more galaxies, but entire domains of reality with different physics, different laws, different fates. And we are isolated inside our bubble, staring at the walls, wondering what exists on the other side. But the walls are not physical, they are informational, and that distinction changes everything. Because the true boundary of the universe is not spatial, it is structural. And understanding that requires confronting the geometry of space-time itself. Space is not what you think it is. It is not a fixed stage. It is not an empty container holding galaxies and stars. Space is a fabric, a geometry, a dynamic structure that bends, warps, and curves in response to matter and energy. General relativity proved this. Mass tells space-time how to curve. Curved space-time tells mass how to move. But the curvature is not just local. It is global. The entire universe has a shape, a topology, a geometry that determines whether space is finite or infinite, bounded or unbounded. There are three possibilities: flat space, positively curved space, negatively curved space. Each geometry produces a radically different cosmos. Flat space is Euclidean. Parallel lines stay parallel forever. The angles of a triangle sum to 180 degrees. Space extends infinitely in all directions. This is the universe of basic geometry, the space we imagine when we think of emptiness. If the universe is flat, it is infinite. No edge, no boundary, no end. Positively curved space is different. It curves back on itself like the surface of a sphere. Parallel lines eventually converge. The angles of a triangle sum to more than 180 degrees. A universe with positive curvature is finite but unbounded. You can travel in a straight line forever and never hit a wall. Eventually, you return to your starting point. The cosmos is closed, finite in volume, but it has no edge because every direction curves back. Negatively curved space curves outward like a saddle. Parallel lines diverge. The angles of a triangle sum to less than 180 degrees. A universe with negative curvature is infinite, but its geometry is hyperbolic, alien, counterintuitive. Space extends forever, but distances behave strangely. Objects appear smaller than they should. Light paths bend in unexpected ways. So which is it? Measurements suggest the universe is flat, or very close to flat. The cosmic microwave background, the distribution of galaxies, the large-scale structure, all point to zero curvature within measurement error. Flat means infinite. Infinite means no edge. The universe extends forever. There is always more space beyond any boundary you can imagine. But there is a loophole. Topology. A flat universe can still be finite if it has a non-trivial topology. Imagine a video game where walking off the right edge of the screen makes you reappear on the left edge. The screen is flat, but it is also finite because it loops back on itself. The universe could work the same way. Flat geometry, but twisted topology. Space wraps around, a three-dimensional torus. You travel far enough in one direction, and you return to where you started. Not because space curves, because space connects to itself. Some cosmologists searched for evidence of this topology in the cosmic microwave background. If space wraps, we should see repeated patterns. The same galaxies appearing in multiple directions, light traveling around the universe multiple times, creating duplicates. The searches found nothing. No repeated patterns, no duplicates, no evidence of wrapped space. Either the universe is too large for the wrapping to be observable, or space does not wrap at all. It is simply infinite. An infinite universe has disturbing implications. If space goes on forever, then every possible configuration of matter must occur somewhere. The number of ways to arrange atoms is finite for any given volume. But if space is infinite, then every arrangement repeats infinitely many times. There is another Earth, another you, identical in every detail. Reading these words right now, an infinite number of yous, scattered across infinite space, living identical lives, and also infinite variations. Versions of you who made different choices, versions where history unfolded differently, versions where the laws of physics are slightly altered. This is not philosophy. This is mathematics. Infinite space plus finite configurations equals infinite repetition. The only way to avoid this conclusion is to argue that the universe is finite. But if it is finite, it must be closed, curved, bounded, and the data says it is flat. The contradiction haunts cosmology. Flat usually means infinite, but infinite means repetition. And repetition feels absurd. Black holes add another layer of strangeness. Every black hole hides a singularity, a point where space-time curvature becomes infinite and the laws of physics break down. Some theorists propose that singularities are gateways, tunnels, wormholes connecting our universe to other regions of space-time, or even to other universes entirely. The math allows it. General relativity permits solutions where black holes connect to white holes, regions of space-time that expel matter rather than consuming it. Our universe could be the white hole output of a black hole in a parent universe, and every black hole in our universe could be giving birth to child universes. This is the cosmological natural selection hypothesis. Universes reproduce through black holes. Each new universe inherits slightly mutated physical constants. Over time, the multiverse evolves toward universes that maximize black hole production. Our universe produces many black holes. That is why we exist. That is why the constants are what they are. We live in a cosmos optimized for black hole formation. The theory is speculative, untestable, but mathematically consistent. The fabric of space-time itself might not be fundamental. Quantum gravity theories suggest space emerges from something deeper. At the Planck scale, distances smaller than 10 to 35 meters, space-time might dissolve into quantum foam, a seething chaos of fluctuating geometry. Space and time are not continuous. They are discrete, pixelated, made of indivisible units. The smooth fabric we experience is an illusion, a large-scale approximation of something granular and quantum at the smallest scales. If space-time is emergent, then the concept of beyond loses meaning. There is no space beyond space, no time beyond time, only the quantum structure from which space-time emerges. The edge of the universe is not a place. It is a breakdown of the classical concepts of space and time themselves, and that breakdown points to the most radical possibility of all. That reality is not made of space, time, matter, and energy. It is made of information, pure information. And the universe is not a physical structure. It is a hologram. The universe is mostly invisible. 95% of the cosmos is made of substances we cannot see, cannot touch, cannot directly detect. Only 5% is ordinary matter, the atoms that make up stars, planets, and everything we know. The rest? Dark matter and dark energy. Two cosmic mysteries that dominate reality and determine the fate of everything. Dark matter makes up 27% of the universe. It does not emit light. It does not absorb light. It does not interact with electromagnetic radiation at all. We know it exists only because of its gravitational effects. Galaxies rotate too fast. The visible matter is not enough to hold them together. They should fly apart, but they don't. Something invisible provides extra gravity: dark matter. Galaxy clusters show the same pattern. The visible galaxies are not massive enough to explain the gravitational lensing, the bending of light around the cluster. Something else is there. A massive halo of invisible matter surrounding the visible galaxies. Dark matter forms the scaffolding of the universe, the cosmic web, the large-scale structure that galaxies cling to. Without dark matter, galaxies would never have formed. The universe would be a thin, cold gas expanding forever. But what is dark matter? Unknown. Physicists propose candidates: WIMPs, weakly interacting massive particles; axions, sterile neutrinos; primordial black holes. Experiments deep underground search for dark matter collisions. Particle accelerators try to create it. Telescopes scan for indirect signals. So far, nothing. Dark matter remains invisible, undetected, mysterious. It is everywhere, in this room, passing through your body right now, but it does not interact. It just gravitates. Dark energy is worse. It makes up 68% of the universe. It is not matter. It is not a particle. It is a property of space itself. Empty space has energy, vacuum energy, and that energy pushes outward, driving the accelerated expansion of the cosmos. The more space expands, the more dark energy appears. More dark energy means faster expansion. It is a runaway process. Dark energy was discovered in 1998 by studying distant supernovae. Type Ia. Supernovae are standard candles. They explode with a known brightness. By measuring how dim they appear, astronomers calculate distance. The distant supernovae were dimmer than expected, farther away. The universe was not just expanding, it was accelerating. Gravity should slow expansion. Instead, something was speeding it up. Dark energy. The leading explanation is the cosmological constant, Einstein's old fudge factor. Einstein added a constant to his equations to keep the universe static. Then Hubble discovered expansion. Einstein called the constant his biggest blunder. But it turns out the constant was real. It represents the energy density of empty space. Vacuum energy. The problem? The observed value is 10^120 times smaller than quantum field theory predicts. This is the worst prediction in the history of physics. The cosmological constant problem. Something is deeply wrong. Either quantum field theory is missing something fundamental, or dark energy is not vacuum energy. It could be a new field, quintessence, a dynamic energy that changes over time. Recent observations suggest dark energy might be weakening. If true, it changes the fate of the universe entirely. The acceleration could slow, stop, even reverse. The universe could collapse in a big crunch. But most data still supports a constant dark energy. Constant means eternal acceleration. Eternal acceleration means isolation. Galaxies beyond the cosmic event horizon are already lost. In trillions of years, every galaxy at all outside the local group will vanish. The Milky Way, Andromeda, and a few dozen dwarf galaxies will merge into a single massive elliptical galaxy. Everything else, gone. Beyond the horizon, unreachable. Future astronomers in that distant era will look at the sky and see nothing. No distant galaxies, no cosmic microwave background, no evidence of the Big Bang, no evidence of expansion. They will conclude the universe is small, static, eternal. A single galaxy surrounded by infinite darkness. All the evidence we have today will be erased by cosmic expansion. Future civilizations will be cosmologically ignorant, and they will have no way to know. Dark energy determines the boundary of the observable universe. It sets the cosmic event horizon. It isolates us from the rest of reality. Dark matter determines the structure within that boundary. It shapes galaxies, clusters, the cosmic web. Together, they control 95% of the cosmos. And we understand neither. The physics screams that something is missing. Some deeper principle. Some hidden mechanism. Maybe dark matter and dark energy are not separate phenomena. Maybe they are two aspects of the same underlying reality. Maybe gravity itself is wrong. Modified gravity theories attempt to explain cosmic acceleration without dark energy. None have succeeded fully. Maybe quantum mechanics and general relativity are both incomplete. Maybe the unified theory, quantum gravity, will explain dark energy as an emergent property of space-time. Or maybe the answer is simpler. Maybe we are not asking the right question. Maybe the edge of the universe, the horizon we cannot cross, is not a limitation of observation. Maybe it is a fundamental feature of reality itself. Maybe the universe is not just larger than we can see. Maybe it is structured in ways we cannot imagine. And understanding that structure requires abandoning classical notions of space, time, and boundaries entirely, because the cutting edge of physics suggests something radical. The universe might not be a three-dimensional space at all. It might be a two-dimensional hologram. And everything we experience, every galaxy, every star, every atom, is a projection from a distant boundary we can never observe. We are blind, not because the universe is dark, because our technology has limits. The most powerful telescopes ever built can only see so far. The James Webb Space Telescope, launched in 2021, peers deeper into space than anything before it. It detects infrared light from galaxies formed just 200 million years after the Big Bang. But even Webb cannot see beyond the cosmic horizon. No telescope ever will. The observable universe has a hard limit, 46.5 billion light years. Beyond that distance, light has not had time to reach us. No instrument, no matter how advanced, can see farther. The cosmic event horizon imposes an even stricter limit, 16 billion light years. Galaxies beyond that boundary are receding faster than light can travel through expanding space. They are lost forever. But telescopes are not our only tool. Gravitational waves offer a new window. When massive objects like black holes or neutron stars collide, they create ripples in space-time itself. These ripples travel at the speed of light, carrying information about events across the cosmos. The LIGO and Virgo detectors have already observed dozens of gravitational wave events. Future detectors will be more sensitive, capable of detecting waves from farther away, from earlier in cosmic history. Gravitational waves could reveal the universe before light could travel freely, before the surface of last scattering, before the cosmic microwave background. Light from that era is trapped, scattered by the opaque plasma of the early universe. But gravitational waves pass through plasma unimpeded. They carry information from moments after the Big Bang, from epochs we can never observe with light. The planned LISA mission, a space-based gravitational wave observatory, will search for these primordial signals. Neutrinos offer another probe, These ghostly particles barely interact with matter. They pass through entire planets without slowing down. Neutrinos from distant supernovae, from black hole accretion, from cosmic ray collisions, stream through space carrying information. Neutrino telescopes like IceCube, buried deep in Antarctic ice, detect occasional flashes from neutrino collisions. Future neutrino observatories will map the high-energy universe, revealing sources invisible to optical telescopes. But all these tools face the same fundamental barrier: the speed of light, the expansion of space, the cosmic horizons. We can improve our instruments. We can detect fainter signals, more distant sources, earlier epochs. But we can never see beyond the event horizon. We can never observe regions of space receding faster than light. The universe imposes a limit on observation, a boundary not of space but of information. The cosmic microwave background is the ultimate wall. Beyond it lies the opaque plasma of the early universe, impenetrable to light. We see the CMB in every direction, a perfect sphere surrounding us. It is the baby picture of the cosmos, taken 380,000 years after the Big Bang. Earlier than that, darkness, not because nothing existed, because light could not travel. Future telescopes will push closer to this wall. The Square Kilometre Array, a radio telescope network spanning continents, will map the cosmic dark ages, the era before the first stars formed. The extremely large telescope, with a mirror 39 meters across, will detect individual stars in distant galaxies. The Roman Space Telescope will survey vast regions of sky, mapping billions of galaxies. But none of these instruments will see beyond the horizons. They will refine our map of the observable universe. They will not expand it. Some physicists propose alternatives. If faster-than-light travel is possible, we could outrun the expansion and reach regions beyond the event horizon. Wormholes, hypothetical tunnels through space-time, could connect distant regions. Alcubierre drives, theoretical engines that warp space itself, could move a spacecraft faster than light without violating relativity. But these ideas require exotic matter with negative energy density, substances that probably do not exist. The universe does not seem to allow shortcuts. Another possibility: signals from advanced civilizations. If intelligent life exists beyond our horizon, and if they possess technology far beyond ours, they might have found ways to communicate across cosmic distances. Wormhole networks, entangled particles, quantum communication channels. Speculative, yes. Impossible, no. SETI, the search for extraterrestrial intelligence, scans the sky for artificial signals. So far, silence. But the search continues. The brutal truth is this: technology cannot save us. We are trapped inside the observable universe by the laws of physics. The edge is not technological, it is fundamental. The speed of light, the expansion of space, the age of the cosmos. These factors define an absolute boundary to observation. We can build better telescopes. We can detect fainter signals, but we can never see beyond the horizon. The universe hides most of itself from us, forever. And that leads to the deepest question. If we can never observe what lies beyond, does it matter? If a region of space is forever unobservable, does it even exist in any meaningful sense? Philosophy crashes into physics. Observation defines reality in quantum mechanics. Does the same principle apply to cosmology? If we can never see beyond the horizon, is the universe beyond the horizon real? And if the answer is yes, how do we know? How do we prove the existence of something we can never observe, measure, or interact with? That question forces us to confront the limits not of technology, but of knowledge itself. What does it mean to exist in a universe with no edge? The question haunts philosophy as much as physics. For thousands of years, humans believed the cosmos was finite, bounded, enclosed. The celestial sphere gave structure to reality. It defined up and down, inside and outside, here and there. Removing that boundary did not just change cosmology, it changed psychology. It changed our sense of place in existence. An infinite universe is incomprehensible. The human mind cannot grasp infinity. We evolved to understand finite spaces, rooms, landscapes, territories. Infinity feels abstract, meaningless, overwhelming. It removes reference points. There is no center, no edge, no special location. Every point in an infinite universe is equivalent to every other point. You are nowhere in particular. Everywhere is nowhere. This realization destroyed the geocentric worldview. Earth was not the center of the universe. The sun was not special. The Milky Way is one galaxy among hundreds of billions. The observable universe is one bubble in a possibly infinite cosmos. We are not at the center. We are not unique. We occupy no privileged position in space or time. The universe does not care about us. It was not built for us. We are a local accident, a statistical fluctuation, a temporary pattern in the flow of matter and energy. The philosophical impact is brutal. Meaning, purpose, significance, all the concepts humans built their lives around have no cosmic foundation. The universe is indifferent. It expands, evolves, and will eventually die, regardless of whether we exist. Galaxies will disperse, stars will burn out, black holes will evaporate. In 10, 100 years, the cosmos will be cold, dark, empty. Everything we build, everything we achieve, everything we are, will vanish without a trace. Existentialism emerges from this cosmic insignificance. We create our own meaning. We define our own purpose. The universe gives us nothing. We must make our own significance in a cosmos that offers none. Some find this liberating. If the universe imposes no meaning, then we are free to choose. Others find it terrifying. If nothing matters cosmically, does anything matter at all? But there is another perspective. The lack of an edge means the universe is larger, richer, more complex than we can imagine. If space is infinite, then every possible configuration of matter exists somewhere. Not just other Earths, not just other versions of you, but entire civilizations, entire histories, entire worlds with physics we cannot conceive. The cosmos is not empty. It is teeming with possibility, infinite possibility. This realization shifts the question. We are not asking, are we alone? We are asking, how much company do we have? In an infinite universe, intelligent life must exist elsewhere. The question is not whether, it is where, how far, and whether we will ever make contact. The cosmic event horizon isolates us from most of reality. Civilizations beyond that boundary will never be reachable, but civilizations within the observable universe, they could exist. They could be detectable. The Fermi paradox becomes more acute. If the universe is so large, so old, so full of stars and planets, where is everyone? Billions of galaxies, trillions of stars, countless planets, and yet silence. No radio signals, no megastructures, no evidence of advanced technology reshaping the cosmos. Either intelligent life is rare, or it destroys itself, or it hides, or we are looking in the wrong places. The anthropic principle offers a disturbing answer. We observe a universe capable of supporting life because we exist to observe it. If the universe were different, if the constants were even slightly altered, we would not be here to ask the question. The cosmos appears fine-tuned for life not because it was designed, but because we can only exist in the tiny fraction of possible universes where the constants allow complexity. This is observer selection bias. We see a habitable universe because uninhabitable universes have no observers. But if the multiverse is real, then our universe is just one among infinite variations. Most universes are sterile, dead, lifeless. We live in a rare bubble where stars form, planets coalesce, and chemistry becomes biology. We are not special, we are lucky. Statistically inevitable across infinite trials, but vanishingly rare in any given sample. The lack of an edge also means the universe has no outside. There is no external vantage point from which to view the cosmos. We are inside, we are part of the system. We can observe, measure, and map the universe, but we can never step outside it. We can never see it as a whole. We can never know its true structure. The universe is like a fish trying to understand the ocean. The fish is made of water. It lives in water. It has no concept of outside the ocean. We face the same limitation. This is the cosmic perspective. We are small, temporary, insignificant on the scale of space and time. But we are also observers. Conscious entities capable of understanding the cosmos, of mapping its structure, of asking questions about existence itself. We are the universe trying to understand itself. We are matter that has become aware. That is not meaningless. That is extraordinary. The absence of an edge does not diminish us. It expands possibility. It suggests the cosmos is richer, stranger, more wondrous than any bounded universe could be. And it forces us to confront the ultimate mystery. Not what lies beyond the edge, but why there is anything at all. Why does the universe exist? Why these laws? Why this structure? And why are we here to witness it? Those questions have no answers, yet. But the search for answers drives science, philosophy, and the human need to understand. And that search leads to the most radical ideas ever proposed about the nature of reality itself. Reality might not be real. The universe you experience, the space you occupy, the time you measure, could be a simulation running on hardware in a higher dimension. This is the simulation hypothesis. And it is not science fiction. It is a testable proposition emerging from physics, computer science, and cosmology. The logic is simple. If it is possible to simulate a universe, then advanced civilizations will eventually create simulations. If simulations are possible, then simulated universes will vastly outnumber the original base reality. There is only one base reality, but there could be billions, trillions, infinite simulations. If you exist, and if simulations are possible, then you are statistically more likely to be in a simulation than in base reality. The odds are overwhelming. Physicist Franco Vazza recently proposed a physically realistic simulation hypothesis. He argues that advanced civilizations could simulate universes by exploiting quantum computing and black hole thermodynamics. The information content of a region of space is proportional to its surface area, not its volume. This is the holographic principle. A two-dimensional boundary contains all the information needed to describe a three-dimensional volume. A sufficiently advanced civilization could encode a universe on the event horizon of a black hole and run the simulation using Hawking radiation as computational output. This is not metaphysics. This is physics making testable predictions. If we live in a simulation, there should be artifacts, glitches, limitations imposed by finite computational resources. Cosmological observations might reveal quantization, pixelation at the smallest scales. The Planck length, 10 ul to 35 meters, might not be a fundamental limit of nature. It might be the resolution limit of the simulation. Anomalies in the cosmic microwave background, unexpected correlations in large-scale structure, violations of Lorentz invariance at high energies, all could be signs of a simulated cosmos. Astrophysical constraints already limit some versions of the simulation hypothesis. A recent RxIve paper calculated the computational resources required to simulate the observable universe at various resolutions. Full quantum simulation of all particles? Impossible. The information content exceeds the computational capacity of anything that could fit inside the observable universe. But coarse-grained simulations, feasible. Rendering only observed regions in high detail, like a video game. Possible. The simulation could be optimized, computing only what is measured, leaving the rest in a probabilistic superposition. The holographic principle goes deeper. It suggests the universe is not three-dimensional at all. Everything we experience, every galaxy, every star, every particle, is a projection from a two-dimensional surface at the edge of space. This is holography. The three-dimensional universe is a hologram encoded on a distant two-dimensional boundary. All the information in a volume of space is contained on its surface. This principle emerged from black hole thermodynamics. The entropy of a black hole is proportional to the area of its event horizon, not its volume. Information about everything that fell into the black hole is stored on the surface, not in the interior. If this applies to black holes, it might apply to the entire universe. The cosmos could be a hologram, a three-dimensional projection of information encoded on a distant cosmic boundary we can never observe. Experiments are testing this. Holographic noise fluctuations arising from the granular structure of the holographic boundary should appear in precise measurements. The GEO 600 gravitational wave detector in Germany reported anomalous noise consistent with holographic predictions. Other detectors saw nothing. The evidence is ambiguous. But the fact that holography makes testable predictions means it is science, not philosophy. Wormholes offer another radical possibility. Einstein's equations allow solutions where space-time folds back on itself, creating tunnels connecting distant regions. A wormhole could link 2 points in our universe separated by billions of light years. Or it could connect our universe to another universe entirely. Traversable wormholes require exotic matter with negative energy density. Quantum field theory allows this. Casimir effect, Hawking radiation, both involve negative energy. But stabilizing a wormhole large enough for a spacecraft, that requires amounts of exotic matter that probably do not exist. Some physicists propose wormholes as the structure connecting the multiverse. Each bubble universe in eternal inflation could be linked to others via wormhole networks. Black holes in our universe could be the entrances. White holes in other universes could be the exits. Matter falling into a black hole does not hit a singularity. It passes through a wormhole and emerges in another cosmos. Our universe could be the interior of a black hole in a parent universe. Every black hole in our universe could contain a child universe. This is the fecund universe hypothesis. Universes reproduce. Black holes are the mechanism. Each new universe inherits slightly mutated physical constants. Natural selection operates on the multiverse level. Our universe exists because it is optimized for black hole production. The constants are fine-tuned, not by a designer, but by cosmological evolution across generations of universes. It is speculative, untestable with current technology, but mathematically consistent. Quantum entanglement suggests another radical idea. Entangled particles share a connection that transcends space. Measuring one particle instantly affects the other, no matter the distance. Some theorists propose that space-time itself emerges from entanglement. Space is not fundamental. It is a network of quantum correlations. Entanglement stitches particles into a geometric structure we perceive as three-dimensional space. Severing entanglement destroys space. Creating entanglement creates space. The fabric of reality is woven from quantum information. If this is true, then the edge of space is not a place. It is a limit of entanglement. Beyond the cosmic horizon, particles in our observable universe are not entangled with particles in distant regions. The entanglement network has boundaries. Those boundaries define the edge of our space-time. What lies beyond? Other entanglement networks, other space-times, other universes. They exist, but they are not connected to ours. They are separate realities, isolated by the absence of quantum correlations. These ideas sound insane. Simulations, holograms, wormholes, entanglement networks. But they emerge from the mathematics of successful theories: general relativity, quantum mechanics, thermodynamics, string theory. They make predictions. Some are testable. If any of these ideas is correct, the implications are staggering. Reality is not what it seems. Space is not fundamental. The universe is not a container. It is a process, an emergent phenomenon arising from deeper structures we are only beginning to understand. And that realization brings us full circle. What lies beyond the edge of space? The question assumes space has an edge. It does not. What lies beyond the observable universe? More space. Possibly infinite space. What lies beyond the multiverse? Other multiverses. What lies beyond reality? Information. Quantum correlations. Mathematics. The substrate from which existence itself emerges. The answer changes everything because it reveals the universe is not a place. It is a pattern. And we are part of that pattern, briefly aware, momentarily conscious, asking questions about the structure of everything. Stand at the edge of the ocean. Look at the horizon. Water meets sky. You see the boundary. But you know it is not real. You know there is more ocean beyond. You know the edge is an illusion created by the limits of your vision, not a wall where water stops. The universe works the same way. The cosmic horizon is not where space ends. It is where our view ends. For thousands of years, humans asked the wrong question. Where does the universe end? What lies at the edge? But the universe has no edge. Space does not stop. It does not have walls. It does not conclude at some distant boundary where existence gives way to nothing. The ancient dream of a celestial sphere, a cosmic shell enclosing reality, was beautiful. It was comforting. It was wrong. The true answer is more profound, more unsettling, more wondrous, than any edge could be. The universe is not a place. It is a process, an evolution, a structure that expands, curves, evolves across billions of years. The edge you seek is not spatial. It is informational, not where space ends, where knowledge ends. We are trapped not by walls, but by horizons, not by the limits of space, but by the limits of light, time, and observation. The observable universe is 93 billion light-years across. Beyond that sphere lies more cosmos, vastly more, perhaps infinitely more. We will never see it. The speed of light forbids it. The expansion of space forbids it. Dark energy accelerates galaxies beyond our reach, severing them from observation forever. Every second, more of reality slips beyond the horizon. Every second, the universe becomes more isolated, more lonely, more unknowable. But here is the revelation. The fact that we cannot observe something does not mean it does not exist. The fact that we cannot reach something does not mean it is not real. Beyond our horizon lie galaxies we will never see, stars we will never map, civilizations we will never meet. They exist. They are as real as anything within our bubble. The cosmos is larger than observation. Reality exceeds measurement. And if reality exceeds measurement, then the universe is not just what we observe. It is what we infer, what we calculate, what we imagine. The multiverse is not visible, but the mathematics of inflation predicts it. Other universes are not observable, but the logic of eternal inflation requires them. We cannot see beyond the cosmic horizon, but the cosmological principle demands more space exists there. Science is not just observation. It is reasoning from observation to conclusions about the unobservable. This is the power and the tragedy of consciousness. We are aware of our limits. We know the universe is larger than we can see. We know most of reality is hidden, unreachable, forever beyond our grasp. Animals do not know this. A dog does not wonder what lies beyond the horizon. A bird does not question the edge of its observable world. Only humans carry the burden of knowing there is more, infinitely more, that we can never access. But this burden is also a gift. Knowing the universe is larger than we can see means knowing we are part of something incomprehensibly vast. Knowing we are not at the center means knowing there is no center. Every point in space is equivalent. You are not nowhere. You are everywhere. You occupy a position in the cosmos as valid as any other. The universe does not have a privileged location, so neither do you. We are small, temporary. A brief flicker of awareness in a cosmos that existed billions of years before us and will continue trillions of years after we are gone. The stars will burn out. The galaxies will disperse. Black holes will evaporate. In the end, the universe will be cold, dark, empty. Everything we build will vanish. Everything we know will be forgotten. The cosmos will not remember us. But right now, in this moment, we are here. We are conscious. We are asking questions. We are mapping the cosmos, decoding its structure, revealing its secrets. We are made of atoms forged in stars, scattered by supernovae, assembled by gravity into planets and life and thought. We are the universe observing itself. We are matter that has become aware. We are the cosmos trying to understand its own existence. That is not meaningless. That is extraordinary. In a universe governed by entropy, by decay, by the relentless march toward disorder, we are islands of complexity. In a cosmos that trends toward cold and darkness, we are warmth and light. In a reality that has no inherent purpose, we create meaning. We make art. We build civilizations. We love. We dream. We ask why. The edge of space is not a place you can reach. It is a limit you can transcend. Not physically, intellectually, imaginatively. We cannot see beyond the cosmic horizon, but we can think beyond it. We can calculate what lies there. We can infer the structure of the unobservable universe from the laws of physics we observe here. We can imagine the multiverse, the entanglement networks, the holographic boundaries, the simulated realities. We can ask whether the universe is infinite, whether it loops back on itself, whether it has a shape we cannot perceive. This is humanity's greatest power. Not strength, not speed, not survival. Imagination. The ability to conceive of what we cannot see, to reason about the invisible, to build models of reality that extend beyond direct experience. Every scientific theory is an act of imagination. Every equation is a map of the unobservable. Every experiment is a test of whether our imagination corresponds to truth. The ancient astronomers imagined the celestial sphere. They were wrong, but they were asking the right question. What is the structure of the cosmos? Where do we fit within it? Modern cosmology answers with horizons, with expanding space, with dark energy and dark matter, with multiverses and holography. We are still asking the same question. We have better tools, better data, better theories. But the question remains, what is the universe? And what does it mean to be part of it? The answer is this: the universe does not end. Space does not stop. Reality is larger, stranger, more complex than we can fully grasp. But we can touch it with mathematics, with observation, with thought. We can map the observable cosmos. We can infer the unobservable. We can imagine the structure of everything. And in doing so, we transcend our limits, not physically, but intellectually. We reach beyond the horizon, not with spacecraft, but with equations. We see beyond the edge, not with telescopes, but with minds. You are not just a body on a planet orbiting a star in a galaxy lost in a vast cosmos. You are a pattern of information, a configuration of matter that thinks, that questions, that wonders. You are the universe aware of itself. And for a brief moment in cosmic time, you can look at the stars, contemplate the horizons, and ask what lies beyond. The answer changes everything because it reveals the truth. There is no beyond. There is only within. We are inside the universe. We are part of it. We are it. And the edge we seek is not out there. It is in here, the boundary of knowledge, the frontier of understanding, the ultimate horizon, the one we spend our lives trying to cross.